So in the previous video we have derived a form of the, or we came at a certain form of the shift operator, which we will be able to use to specify the initial condition for our evolution. So shift operator is an important thing here. And the shift operator looks like this. It's characterized by the amount of the shift, and it's an exponential of I q0, and now here is the operator of the momentum. This will specify our initial condition, and in order to be able to do something with it, we have to actually use that initial condition in some differential equation to solve the time evolution. Before we do that, I will sketch the way how we will actually come to some matrix elements for this. So our way will be realizing that both Q and P can be written in terms of so-called creation and annihilation operators. This is a topic of another video. And here we have, so Q is a sum of the creation and annihilation operator, and P is I divided by square root of 2 and a difference between these two guys. Now this is a piece of knowledge that has to come from somewhere else and is usually presented in some quantum mechanical courses. So we will have the exponential of I q0 p expressed in terms of exponential over minus q0 divided by square root of 2, and here is a plus minus a. And the thing that enables us to do something with this is another piece of knowledge from basic quantum mechanics, and that is the action of these two operators on the eigenstates of the harmonic oscillator, namely annihilation operator when applied to a nth state of the harmonic oscillator decreases its state number. So I'm getting a lower state multiplied by a factor square root of n, and if I act the same way on the same state by a creation operator, I'm getting square root of n plus 1 and the n plus 1 state. So this is a state lowering operator, this is a state raising operator. And now the whole question is, how do I use this in representing my initial condition and my time evolution. So let's start with the initial condition. Initial condition is fairly simple, so it's a Q representation of the dq psi g, and that could be written in terms of the now representation using the eigenstate. So here I have the Q, here's the eigenstate, and dq0 psi g. So that's all I need, because in fact here are my psi and q's. So these things, they show how this wave function, how this representation, how this initial wave function looks like in space. And here I have the the representation of the shifted wave function in terms of these eigenstates. This can be sort of further expressed in more suitable way, so I will put few more equals here. So this here is my initial condition that I already said is psi 0 q, and this is the same equal sign as here because I have also equal from here to here, and that is sum, maybe let's use this white color, sum over n psi and q, let's write it this way, that's this thing, and here I have the matrix representation of the tq0 and an additional index m and m here, and here I would have m psi g. So this would be the representation of the ground state. So this would be the function psi. Well, this can be only, in fact this only can be one coefficient. This is the ground state q, and because the m is present here, so I have to also have here, but it's in Kronecker delta with the 0. It can only be the ground state. So writing this a little bit more farther, we can write that the initial condition now in space is sum over n. This is a representation of nth state. Here I have the shift operator now represented completely in terms of the matrix elements in the eigenstates, and well, sorry, this thing has to be 0, so there is a 0th element of this shift operator here, and here I have the psi g. No, this is all wrong. This is a representation, sorry for that confusion. So this is a number. This is a this is something else. This is the CNG, or this is CG and delta mg. So this has only one element, and if we assume that at the beginning, or that the function that we shift is really the ground state one, then there has to be 1 here. So I will not write here anything. So this is the initial condition. Now this is the initial condition, how it's going to look like in space. So the funny thing is that we started with the wave function that was sitting here at the bottom, and it was really just one state out of the many possible states of the harmonic oscillator. And now when I shift that and put the same wave function up here, it looks like a superposition of all the states, in fact, with some weighting factors that are here. And now how the time evolution is going to look like. Time evolution. Well, the time evolution in space, so it's q, no, this is just the total already, not only the initial condition, that's at all times t. Well, this will be the initial condition as it is with the so initial condition was this psi g, and with the evolution operator put in front of it. Now I can use the same representation as before, so it should be n m, and here I would have the q, because this is already a representation in terms of q, and here I can have n and n, that's the one unity, and the other unity will be again m written in here. Well, I would also need another representation of unity in order to be able to find to work with the elements of this evolution operator. So altogether I will have n m k q n, and now n u t k k dg0, and here we have m and m psi g. Here again we would say that m has to be equal 0, because this is the ground state, this is the 0 in fact. So the time evolution will need only two indices, m and k, no, n and k, and here we again replace the q, the psi and q q, that's this thing. Here the elements n, u, t, k, k, d, d, q0, sorry, it should not be g, q0, 0, and this we said is 1. This we said is 1. And now I can also use another nice property of the fact that these guys are, these k and m's, they are eigenstates of the evolution operator. I can say, well, in that case, the matrix, the evolution operator, which is the matrix of minus I exponential of minus I divided by hr Hamiltonian t, is also diagonal. So I'm getting sum over, so now k and l have n have to be the same, so I'm basically stuck with just n, psi, and q. That's how it looks in space. Here I have the diagonal elements n of this exponential, the evolution operator, and n again, and here I also have just n d g0 0. So it seems that the only thing I really need is now are these elements, which it will turn out to be that they are very simple, and these elements here, which will not be so simple to find. We will find them numerically, but that's the only thing that we will need to find numerically. Everything else will be given to us, or almost analytically. Okay, so let me summarize. Psi qt, this is how the wave function looks like in space, and that is, well, we first have to find out what is this. Alright, so this is the diagonal elements of such a of this operator, and we are working in the diagonal basis. So on the diagonal of the Hamiltonian matrix there will be only energies, and these represent therefore just the exponentials of this with the energy. So minus I divided by h bar epsilon n d. Yeah. Now, of course, we also know what's the energy of the nth state of the harmonic oscillator. If we ignore the ground state, what these zero phonon energies, which we could actually ignore here because we can set the energy wherever we want, and we set that to 0, then we get here e to the power of minus I, and then n by omega, omega being basically epsilon n divided by, or the energetic step of the harmonic oscillator divided by h bar, multiplied by t. So that gives me altogether, here I was a little bit too fast, let's take the space down here. So the psi qt is therefore equal to sum over n. Here are the eigenstates expressed in space, e to the power of minus I n omega t, and here we have the only thing that we really need to find out in some way, and that's these coefficients. That is the matrix elements of our shift operator, and this is going to give us the evolution of the wave function, which we will then plot in one of these demonstrations. Okay, that's enough for now, and in the next video we will already discuss how we will practically calculate this whole stuff and how we will represent this wave function, its time evolution, graphically.